So now we've played with some arithmetic, which we definitely need to have in any type of a serious science course. Why? Well, because we measure things. Need arithmetic for that. Here in astronomy land, we have enormous scales to measure, enormous distances to measure. And one of the toughest things to get our brains wrapped around is just how enormous the universe is. But with the arithmetic that we've done thus far, we can tinker with the numbers a little bit and start to get a feel for it. We can use a little bit of imagination. So let me start. We're going to start on page 26. And I'll start with this idea of universal constants. What are universal constants? Well, the street fighting definition is this: a set of roughly 20 numeric constants that fundamentally determine or describe the universe. So let me jot that down for you. There it is. Universal constants, a set of approximately 20 numeric constants that fundamentally describe or govern or determine the universe. Let's try this. Think of them as an operating system. We've talked about one of them briefly, the universal gravitational constant. We'll get into that in a little more depth. But for the time being, let's just think about one that you're probably more familiar with, the speed of light. That is a universal constant. And let me also add this. When we say that something is a universal constant, that means it's universal. That means it works everywhere in the universe. The speed of light is the same here as it is 10 billion light years away. The universal gravitational constant is the same here as it is 10 billion light years away. There aren't different areas of the universe in which the laws of physics are different. Okay? That's what we're saying. All right, so let's talk about one that we are more familiar with. The speed of light, indicated by the letter C. All right, a couple of different ways that we measure that. One way is 186,000 miles per second. Another way is 300,000 kilometers per second. And one that we'll be using more often is this, 3.0 times 10 to the 8th meters per second. We're going to use that measure when we apply it to a physics formula, or 3. Now, let's pause here and just think about this. How do we wrap our weak, feeble human brains around 186,000 miles per second? And the answer is we don't. And here's why. You have to recognize what the limitations of the human brain are. So let's do a little exercise here. Can you close your eyes and imagine 5 objects? Yeah, probably. How about 10 objects? Sure. Maybe a dozen. How about 20 objects? Yeah, probably you can. What about 100 objects? Can you close your eyes and imagine 100 objects? Well, probably, if you thought about it, if you laid out a grid of pennies, 10 by 10, you'd say, oh, okay, that's what 100 objects would look like. What about 437 things? And the answer is probably not. The human brain just doesn't work that way. And so instead, what we do is we have these symbols that we use, and make no mistake about it, these are crutches, they're tools. But this is how our weak human feeble brains get to manage numbers like this that otherwise we could not manage. We use the symbology of it. Well, okay, that's all well and good, but how do I get a feel for what the speed of light is? Well, again, here's where the imagination part comes in. Let's imagine that from Portland to Boston is roughly 100 miles. Now, maybe it's 107 miles, maybe it's 93 miles, I don't know. But let's just rough it out and say it's an even 100 miles from Portland to Boston. I mention that because most, if not all of you, have had the experience of getting in a car, driving down 95 to get to Boston, and driving back. So a round trip is going to be roughly 200 miles. This is something that you know, most of you probably know intimately. You know what it feels like to sit in that car and go through turnpike traffic and then hitting Boston traffic and all of that stuff. You know what that feels like. Okay, so now the question is, how many round trips to Boston could you do in 1 second traveling at the speed of light? Well, the way to do that is to take the distance traveled at the speed of light, which is 186,000 miles, and then divide it by 200, and we get 930 round trips per second. That's how fast the speed of light is. Almost 1,000 round trips to Boston in 1 second. Now let's recognize something else that the human brain has difficulty with. The passage of a single second. We know what a second is because we're all grown-ups here and we've learned how to tell time and all that good stuff, but really think about the passage of a single second. That becomes a little problematic. But what if I could demonstrate visually what a half second looks like? So the first question is how many round trips could we do traveling at the speed of light in a half second? Well, the solution is to take 930 divided by 2. And we get 465 round trips per a half second. Now, how am I going to demonstrate what a half second looks like? Well, it so happens that here on planet Earth, gravity at the surface of the Earth is such that if I drop an object like this rock here from a height of 4 feet, which is right about here, it will take precisely 0.5 seconds to hit the floor. So here we go. Here's what a half second looks like. All right? You should be able to hear it thump the floor. All right, here we go, 0.5 seconds. There it is. That's a half second. Let me do that one more time. All right, here we go, buckle up. 0.5 seconds. That's a half second. 465 round trips to Boston. and the time it took that rock to get down to the floor from chest high. You can try that at home. All right? So, that's one way of looking at what the speed of light is. Well, let's expand this idea a little bit. Instead of going to Boston and back, let's go around the world. We'll go to page 27. All right, so here we are. Here's planet Earth. This is home. This planet is approximately 8,000 miles in diameter. All right, so that's home for us, an 8,000 mile diameter ball of dirt. So now, what would be the circumference of the Earth, roughly? Well, circumference equals 2 pi r, or pi times the diameter. All right, we're going to rough this one out. Pi, we know, is 3.14, but we're just going to rough it. We're going to round it. So how do you round 3.14? Well, we're going to round the bejesus out of it. We're going to say roughly 3, okay? Just to get a rough idea. So, what would be the rough diameter of planet Earth? Well, 8,000 times 3, the circumference rather. The circumference would be roughly 24,000 miles, give or take. So, how many trips around the world could we do in 1 second traveling at the speed of light? Well, $186,000 divided by 24,000, and that gets us 7.75 times in 1 second. Or, if we wanted to see how far we'd go in a half second, we divide that by half. $3.875 times, just a little under 4 times. So here we go, one more time. Where did the laboratory rock go? Oh, there it is. Okay, so here we go. Buckle up, boys and girls. We're going to go around the world in roughly 4 times in the time it takes this rock to drop. 0.5 seconds. Ready? Here we are. There it is. That's what the speed of light is. Now, I have been around the world 6 times, but it took me 20 years in the United States Navy to do that. So that'll give you an idea of just how fast the speed of light is. Well, let's keep going. Let's think about it. Our nearest celestial neighbor, let's move to page 28. Our nearest celestial neighbor is the moon. And on the top of page 28, you'll see the Earth and the moon drawn to scale. And the distance from here to the moon is approximately 240,000 miles. Now, how is it we're able to see the moon? Well, the sun shines on the moon, that light bounces off the moon, covers 240,000 miles of distance until it hits our eyeballs. The question is, how long does it take that light bouncing off the moon to get here? Well, here's the first physics you ever learned in grade school. Distance equals rate times time. So time equals distance over rate. My distance, 240,000. My rate, 186,000 miles per second. comes out to 1.29 seconds. It takes 1.29 seconds for that light to come from the moon to your eyeball. Oh, but wait, here's this distance of 240,000 miles. How do we wrap our heads around that idea? Well, let's do a little fantasy here. Let's say that we're going to take a field trip to the moon. How are we going to get there? Well, we're going to take a nuclear-powered bus, and there's a secret highway that goes all the way to the moon that the government's hiding from you. But we're going to go on that highway, and it's a nuclear-powered bus so that we don't have to stop for gas. And we're going to load it up with all the DVDs, Doritos, and beer that we need to make the trip. And we're going to drive 24 hours a day, 7 days a week until we get there. And we're going to travel at 100 miles per hour. Why 100 miles per hour? Well, because it's a nice even number. And I know that you know what it is to be in a vehicle going 100 miles per hour. Don't lie, you know you've done it. So, this is easy. Barely need a calculator for this one. It'll take us 2,400 hours to get there, which doesn't mean much to me. So I'm going to divide that by 24, and that means it's going to take 100 days. Right about at the end of the semester. If we leave tonight, we'll get there just about at the end of the semester, give or take. That's how far away the moon is. It is so far away that if you traveled toward the moon 100 miles an hour, 24 hours a day, 7 days a week, it would take you 100 days over 3 months to get there. And yet, it takes light 1.29 seconds to cover that distance. What we try to do in astronomy, oftentimes, is we try to express these ideas in meaningful terms. And you're going to hear me use that phrase a lot. Meaningful terms. 2,400 hours isn't very meaningful. 100 days is. Any chance that we can express something in meaningful terms, that's what we want to do. Because we want to be able to wrap our feeble human brains around the idea. It also means that when you look at the moon, you are not looking at the moon as it is now. You are looking at the moon as it was 1.29 seconds ago. In other words, when you look at the moon, you are looking directly 1.29 seconds into the past. That's what you're looking at. Astronomers call this lookback time. Page 29. Distance from the Earth to the Sun. 93 million miles. Or 9.3 times 10 to the 7th miles. Okay. So, how long, question 7, how long does it take light from the sun to reach the Earth? This is another distance, rate, and time question. So, time equals distance over rate. In this case, 9.3 times 10 to the 7th over the rate, which is 186,000, or 1.86 times 10 to the 5th. And that equals 5.0 times 10 squared seconds, which equals 500 seconds, which isn't very meaningful. So I'm going to put that into something more meaningful. I'm going to divide by 60. And I get 8.333 minutes which is 8 minutes, 20 seconds. It takes 8 minutes, 20 seconds for that light to get here. That means that when you look at a red sunset, you know, those red sunsets where you can look directly at the sun, you are looking at the sun as it was 8 minutes, 20 seconds ago. 8 minutes, 20 seconds ago. You were looking 8 minutes, 20 seconds into the past. Now, in cosmology especially, what we try to do is we try to define reality itself. That's really ultimately what we're doing here. We're defining reality. So, brace yourself. Here's what comes next. Given our 5 senses, it is impossible for us to observe the present. Everything we observe, whether by sight, hearing, touch, taste, or smell, by the time we are aware of it, it's already in the past. It takes time for the sound waves from my voice to go from my pie hole to your ear bones. And then it takes more time for the nerves in your ears to send that impulse to your brain. It takes time for light to cross whatever distance to hit the back of my eyeball and then go down, trigger a response in my optic nerve, which goes to the back of my head, to the visual cortex, thereby triggering what we refer to as sight. It takes time for the sting of slapping my hand to travel up my arm to my brain. It takes time for taste to go through a chemical reaction in my tongue to get to my brain. The same happens with smell, with the olfactory nerves. In other words, it is impossible for us to perceive the present. We can't. We can't. Because of physics and because of physiology. We cannot perceive the present. But we fool ourselves into thinking that we are, and that's primarily, I think, just to keep ourselves from going batshit crazy. But the fact of the matter is, we can never, ever perceive the present. We can't. Moving on. Let's see how far 93 million miles is. Well, how are we going to do that? Well, we'll charter a jet. We'll do that. Don't worry, we'll go at night. So, let's say that a commercial jet averages something like 500 miles per hour. So, 93 million miles. Divided by 500. Oh, that's going to get us to the sun in 186,000 hours. Which means nothing to me. So I'll divide that by 24. And that means I'm talking about 7,750 days. Still kind of meaningless. So I'll divide that by 365. That gets me 21.233 years. Traveling at 500 miles per hour. That's Portland to Miami in 3 hours. That's what 500 miles per hour is. Maine to Florida in 3 hours. And at that rate, it would take us over 21 years to get to the sun. Some of you aren't even that old yet. The sun could blow up right now, and we wouldn't know for another 8 minutes and 20 seconds. Don't worry, it's not going to. It's not that kind of a star. You'll see as we go along. But supposing that it did, it would take 8 minutes, 20 seconds before the light would go out, because it takes that long for the light to get here. Distance to the nearest star. Page 30. The distance to the nearest star is 4.2 light years. A light year, the distance that light will travel in one Earth year. Okay? That star is called Proxima Centauri. Don't worry about looking for him. You can't see him with the naked eye. He's a little tiny red dwarf. Too dim to be seen with the naked eye. You can see him only with very powerful telescopes. But the point is, that is the nearest star to us other than the sun. That is the nearest star to us. It takes over 4 years for the light from that star to get here. It means that when we look at that star, we are looking 4.2 years into the past. 4.2 years. And that means that all the other stars are even further away. Now, I haven't included this in the book, so we'll pause here. I want to just show one other thing to you. Here's a constellation probably most of you are familiar with. Looks kind of like this. Orion the Hunter. People are able to pick him out because of the 3 stars in the row. That's Orion's belt. If you look closely, you'll see that this star has kind of a reddish sort of tinge to it. That is Betelgeuse. It is a red giant. Betelgeuse is roughly 430 light years away. That means that when you look at that star, and now I've shown you how to find him, he's right up here, okay, on Orion's shoulder. When you look at Betelgeuse, and you'll see he's got a little bit of a reddish tinge to him, you are looking 430 years into the past. You are looking directly 430 years into the past. That's look-back time. That's what look-back time is. Another way to think about look-back time is this. Imagine if we could instantaneously transport a team of astronauts roughly 150 light years away from the Earth. And they are equipped with the mother of all telescopes. This telescope is so powerful that they can look back on Earth and they can actually see people walking around on the surface, just like some of the more high-powered telescopes that are used for GPS, all right? So, if we could do that, if we could send that crew of astronauts out there with this humongous telescope to look back at the Earth, what would they see if they could look down and see people on the surface of the Earth? Well, they would be able to watch Abraham Lincoln deliver the Gettysburg Address in real time. They would be able to look directly 150 years into our past. That's what you are seeing. When you look up at the night sky, you are looking directly at the past. Hundreds, and in some cases, thousands of years into the past. In some cases, millions of years. Andromeda Galaxy is the only galaxy outside the Milky Way that can be seen with the naked eye. Andromeda Galaxy is 2.5 million light years away. It looks like a smudge. You've seen beautiful photographs of it, or you probably have. I'll put them up on the website. But to the naked eye, Andromeda Galaxy looks like a smudge, like a little cloud. It's a galaxy 2.5 million light years away. When you look at that smudge in the sky, you are looking 2.5 million years into the past. And so when astronomers say such and so happened 3 million years ago, 10 million years ago, a billion years ago, it's because they can look right at it as it's happening. They can look directly into the past. That's what astronomers do. We look directly into the past. Now, I've been talking about light years. What is a light year? Well, as I said, it's the distance that light will travel in a single year, a single Earth year. So, how many miles are in a light year? Well, we're getting into huge numbers again. So, here's how we can figure this one out. I got 1.86 times 10 to the 5th miles per 1 second. I want to find out how many miles per year. So I'll do a little conversion here. I'll change seconds to hours. And then I'll change hours to days. And then I will change days to years. There are 3,600 seconds in an hour, or 3.6 times 10 to the 3rd seconds in 1 hour. There are 24 hours in a day, or 2.4 times 10 to the 1st power hours in 1 day. There are 365, or 3.65 times 10 squared days in 1 year. So I'll do a little cross canceling here. I'll cross out seconds, I'll cross out hours, and I'll cross out days. So, first I'm just going to multiply the coefficients, just like I showed you. 1.86 times 3.6 times 2.4 times 3.65, and I get 58.657. Now I'll add up the exponents. 5 plus 3 is 8, plus 1 is 9, plus 2 is 11, times 10 to the 11th miles. Now, astronomers are notorious for rounding numbers. So I'm going to round this to 5.9, and I moved my decimal point over to the left, times 10 to the 12th miles. Now if I really want to round it, I'm going to make that 6.0 times 10 to the 12th miles. What's 10 to the 12th? That's a trillion. So in other words, 6 trillion miles. That's what a light year is, 6 trillion miles. Astronomic units that we're going to be using, page 31. Since 1 light year is 6 trillion miles, a mile isn't a very practical unit for an astronomer to use. So we're going to use larger units. The first one we'll talk about is an astronomic unit, or an AU. It's the average distance from Earth to the Sun. Okay, so we already know that that's 93 million miles. But it's also 150 million kilometers, which becomes 1, 2, 3, 4, 5, what's it? 1, 2, 3, 4, 5, 6, 7, 8, 9. And kilometer is 10 to the third. So that comes out to 1.5 times 10 to the 11th meters. It's going to be important for you to know that. One astronomic unit is 1.5 times 10 to the 11th meters. Another item that we use is a parsec. And it's based on trigonometry, and there's an explanation for it on page 31. But in a nutshell, what you need to know is a parsec, which is abbreviated PC, is 3.26 light years. So we're going to be dealing with primarily light years, astronomic units, and parsecs as our units of distance. We're going to have to do some metric prefixes. So you may as well get used to those. The ones we're going to concern ourselves with are giga, or giga if you're fussy about it, mega, kilo, centi, milli, micro, and nano. All of these prefixes are equivalent to powers of 10. Keep that in mind. Giga is 10 to the 9th. Mega is 10 to the 6th. Kilo is 10 to the 3rd. Centi is 10 to the negative 2. Milli is 10 to the negative 3. Micro, 10 to the negative 6. Nano, 10 to the negative 9. Prefixes are equivalent to powers of 10. So that's giga is 1 billion. Mega is 1 million. Kilo is 1,000. Centi, 0.01 or 1/100th. Milli is 0.001 or 1/1000th. Micro, 0.00001 or 1/1,000,000. And nano is 0.00001, 2, 3, 4, 5, 6, 7, 8, 1, yeah. 8001 or 1/1000,000th. Okay, measures of distance. Some conversions that you should know. Okay, so a mile, 1 mile, 5,280 feet, or 5.28 times 10 to the 3rd feet. Why would we be using feet? Well, because when we get into using some of Newton's equations, we're going to have to use feet and meters, standard units. Okay. 1 1 mile is also equal to 1,610 meters, or 1.61 times 10 to the third meters. A meter is the standard metric unit of length. A meter is the standard metric unit of length. Write that down. 1 meter is roughly 39 inches. The standard unit. Standard units. Units of measure that are used in fundamental physics formulas. Write that down. A standard unit is, these are units of measure that are used in fundamental physics formulas. Sir Isaac Newton stuff. These are the units that we're going to have to tangle with whenever we tangle with Sir Isaac. Okay. Now, orders of magnitude is something that we deal with in astronomy. When we talk about orders of magnitude, we're talking about a rise or decrease in exponents. So, for instance, size of a proton is roughly 10 to the negative 15 meters. The distance to the sun, 1.5 times 10 to the 11th meters. So between the two, okay, from 11 to negative 15 is 22 orders of magnitude. Measures of time. When we are using measures of time in fundamental physics formulas, the standard unit will be 1 second. Not minutes, not hours. 1 second. And again, this is what we have to use for Sir Isaac's. Now remember, 3.6 times 10 to the third seconds equals 1 hour. Page 33. Just a quick overview of how to convert prefixes into powers of 10. So, for example, number 1 on page 33, I have 5.26 times, oh, I'm sorry, I'm getting ahead of myself. I have 5.26 kilometers. Now, kilo is the same as 10 to the third, so I can take that kilo and replace it with 10 to the third. So it becomes 5.26 times 10 to the third meters. Example number 2, 6.6 megaparsecs. Right? Mega is 10 to the 6th, so that would be 6.6 times 10 to the 6th parsecs. I have 3,345 kilometers. All right, that's kilo. So now I can make that 3,345 times 10 to the third meters. But if I wanted to get into strict scientific notation, I can bump my decimal point over 3 places to the left, and it becomes 3.345. My decimal point went to the left, therefore the exponent goes up, and it becomes 10 to the 6th meters. All right. Finally, page 34. This is an exercise for you to do. I want you to try this out. So go ahead and hit pause and try these. Give yourself a few minutes to do that. And then hit play. So here we are. I am assuming that you did hit pause, that you did try this out on your own. Example number 1. I got 42.38 light years. How many parsecs would that be? Well, I'm going to divide by 3.26. and I get 13 parsecs. Next example, 4 parsecs is approximately how many AUs? I neglected to mention something here, so we're going to go back to the page where I talked about AUs briefly. And that would be on page 31. So we're going to go back to page 31. Okay. On page 31, there's that diagram that talks about an AU, and it shows that 1 parsec is 206,265 AUs. Well, we're just going to do this. 1 parsec is roughly 200,000 AUs. Okay, so make a note of that. That's close enough because, again, in astronomy we round things all the time. So yeah, know that 1 parsec is roughly 200,000 AUs. So the next example, 4 parsecs would be roughly how many AUs? Well, since 1 parsec is 200,000, so that'll be 200,000 times 4. So roughly 800,000 AUs. 4 parsecs is roughly 800,000 AUs. Okay, so now next one, 20 parsecs equals how many light years? So that's going to be 20 parsecs. We're going to multiply that times 3.26, and we get 65.2 light years. 4.2 megaparsecs. How would we express that in scientific notation? We're going to replace mega with 10 to the 6. Okay, and finally, $380,000 kilometers is going to be how many meters expressed in scientific notation. So we start with 380,000 kilometers. That's going to be 10 to the 3rd. So now I have 380,000 times 10 to the 3rd meters. I'm going to go 1, 2, 3, 4, 5. 5 to the left. If the decimal point goes left, the exponent goes up 5 places. So that will be 3.8 times 10 to the 8th meters. There you go. All right. A little bit of arithmetic to reassess our sense of the scale of the universe. All right. Hope your eyes aren't too glazed over, and hopefully you got yourself going, damn, if we did that, we did a good job. Till next time.